Okay. Welcome back. So just to get this on your radar, exam 2 is going to be a week from Friday. So I think that is the 27th. So we'll talk more about what's going to be on it and stuff like that.
Gonna be on Friday?
Oh, yeah, thank you. Okay, yes. Wednesday, the 25th. Okay, thank you. Wednesday, 3:25. Okay, so on Wednesday of this week, I'll talk about what's going to be on it. It's going to be everything up through, I don't know. I'll talk about that. I'll look at it. And we have been working on internal loads. And we've been talking about it like this. So imagine that we have, yeah, sure. Okay, number 4. Okay, as I look at this, I realize, because I just looked at this with Marco, that the the question on here is worded a little differently than the newest one that I have. So the new one I have says something at the end like use E and new in your calculations. So that makes it a little more clear that, okay, we don't know what those are, but you're just going to use those parameters in the calculation. But okay, we have a cylindrical pressure vessel, and the stresses we have. So we have a pressure in like this, force or stress around the rim like this. Those have to equal each other for this to stay in static equilibrium. So we have the pressure times pi r squared has to be equal to the stress times 2 pi r times the thickness. And so what we get is that the stress is equal to P R over 2T. So that's for the two the two halves stress, the left and right stress. And then for the other one, we have something like this.
And the sigma is stress, right?
Yes. Okay, so this time we have the pressure like this, counteracted by stress in the walls like this. So the area that pressure is acting on is the length times 2 times the radius. So 2 times the radius times the length. And that is equal to the stress times the area of the two metal pieces on the edge. There's two of them. And then it is L times the thickness. And so the L's cancel, the 2's cancel, and here we get stress is equal to PR over T. Okay, so our stress tensor, our principal stress tensor is, we can do this in either order, PR over T, 0, 0, 0 PR over 2T. Okay, and then our,
We also have it the other way around too.
yeah, and then our max shear stress is PR over T, the maximum normal stress, minus the minimum normal stress, which is 0, divided by 2. So you get PR over 2T. So that's the maximum shear stress. Now, the Voigt strain is equal to this big compliance matrix times, I'll just write this as dot, 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 but somewhere in here, there is a shear stress that's equal to PR over 2T. Okay. And the key thing is that, so this represents the Voigt stress. Okay. And in order to get that Voigt strain, we have to multiply this shear element by 2 times 1 plus nu over E. Okay. So the biggest, and the key thing, I guess, is that this whole row is zeros, except for that element 2 times the quantity 1 plus nu over E. Okay, so you can always figure out the shear strain by just multiplying this value, 2 times the quantity 1 plus nu over E, times the shear stress. Okay, that's not true with the normal stresses and the normal strains. Remember, a normal strain is dependent on all 3 normal stresses. We had a problem like that we had to do. But a shear strain is only dependent on the one corresponding shear stress. So anyways, that means that we don't have to fill in this whole matrix. We can just say that our shear strain max is equal to 2 times the quantity 1 plus nu over E times PR over 2T. The 2's cancel. So 1 plus nu times PR over ET. And this could be plus or minus, but we don't care about that. We just want to keep the absolute value less than 1 times 10 to the minus fifth. So now we'll set 1 times 10 to the minus fifth equal to 1 plus nu times PR over E times the thickness. And what we want to get is, what's the smallest wall thickness? We're given all this other stuff. So T is going to stay a variable. Our pressure is 4 times 10 to the 6. That's the inside pressure minus standard atmospheric pressure on the outside. So what's that? 3.899 times 10 to the 6th, something like that. That's our P. And then we have 0.2. Okay. So 1 times 10 to the minus 5 is equal to 1 plus nu times 3.899 times 10 to the 6. I guess be careful that it gives you a radius of this pressure vessel rather than a diameter. I think it said radius. Yeah. So that's 0.2. Divided by ET. And now we want to solve for this T. So T is equal to 1 plus nu times 3.899 times 10 to the 6 times 0.2 over 1 times 10 to the minus 5 T, E. And so the thickness is like 7.798 times 10 to the 10th times 1 plus nu over E.
And what number 3, what do you do mostly the same calculations? Asking for
Shear stress.
It says what the smallest wall thickness the container can have for the maximum shear stress in the wall fit.
Yeah, it's the same. You just don't have to use the Poisson's ratio and Young's modulus.
Okay.
Yep, same idea. Any questions about this one? Okay. Well, that looks like a big number, but remember E is bigger than this, so you're going to end up with, a relatively small thickness. Okay. Any other homework questions you want to see before I I only gave you 3 and 4? Okay. All right, so let's go back to internal loads. So last time what we saw, this is what we've done so far. We've done just a single beam with loads at one end. I'll call this RA, and then loads at the other end. Call this RB. Okay. And what we saw is that we can do cuts. So I'm going to do a bunch of cuts of this, okay? So think of a cut at any location along this beam. Okay, so we can start out with just barely a sliver over here and all this stuff that we're not including. And the loads we have are an RA and a couple MA, and then the internal loads T. Oh, and I didn't, let's put torques in here too. So we have torque A, torque B. Okay, so then here's our torque A. And then we have the internal loads T, V, M, and fancy T. Okay, so that's if we said we want this cut to be at 0.005 meters from the left end. Okay, and then we could do we could cut at a different place. And we would have RA here, fancy torque A, MA, and then we'd have our internal loads T, V, M, and fancy T. And I don't want to like belabor this point, but I guess I'll draw one more. The key is no matter where you do this cut, you get the exact same loads on your free body diagram. So here we still have RA, MA, torque A, and then we have our internal loads T, V, M, and fancy T. Okay. The key is no matter where you make your cut, the free body diagram looks the same. You know, it is the same. So what we do is just do one cut with the length represented by the variable x. And calculate the internal loads as a function of x. Okay, so that's the idea. The strategy changes, though, when you have a point force a point couple, or a change in the distributed load function that's between the two endpoints. Okay, so let's think about this. So let's say that we have a free body diagram, a body that has an RA, an MA, a TA, and then one of these things happening at the midpoint. We could think of it as R mid, but so I'm just going to write it as a force vector like that, but it could be a point couple, or it could be a change in the distributed load function. And then over here we have our RB, MB, and torque B. Okay. Now, up until you get to the midpoint, all the free body diagrams look the same. So if I do this cut, here's our RA, here's our MA, here's our torque A, and then we have our internal loads, T, V, M, and fancy T. Or I could do a slightly longer cut. And here we have RA, MA, torque A, and the internal loads. Okay, these are the same. These free body diagrams are the same.
And both these are happening before the midpoint, right?
Right, exactly. But once the cut passes the midpoint, or it doesn't have to be the midpoint, once it passes the point load, the free body diagrams are different. Okay, so the first one we might do looks like this. We still have our RA. We still have our MA. We still have our torque A. But now we also have that point force, R mid. And then we have our internal loads, our T, V, M, and torque. And then just to complete the set, I'll do one more. So this is RA, MA, torque A, the internal loads, and then we still have that R mid. And these are the same. These free body diagrams are the same. Okay, so every time you have a point force, a point couple, or a change in the distributed load function, you need a new cut. Besides that, the approach is the same. Okay, so I'm going to do an example problem. Yeah.
Can you make a cut at the point load?
No, we can't make the cut at the point load. You have to remember that a free body diagram is always the main thing a free body diagram is doing is deciding what material is in your chosen body and what material is out. And so we need to specify whether the material that's being acted on is in your free body or out of your free body, you know? And so you can do just enough so that you know that that force R is in your free body, or just little enough that you know it's out of your free body. But you can't have it be kind of half in, half out, you know? Okay, so here is the example. So let's say we have a beam that's connected on the right to a pin joint and a roller. And we have an external load of 1,000 newtons and a torque of 200 Newton meters. And let's say that each half of this is 1 meter long. So the whole beam is 2 meters. And we want to calculate the internal loads. So we know that that 1 point force in the middle is going to give us one additional cut that we need to do. So we're going to have to do 2 cuts on this. Let's start by calculating the external loads. And I'm going to assume, now this is something I would have to give you more details about what this roller joint is, but I'm going to assume that this doesn't provide any torque. Okay, so that isn't going to produce, one of these things. Okay, that just depends on the specifics of the joint, and you would have to be given that in a problem.
Would it say how much torque it gave, or we have to calculate that?
You have to calculate it.
Oh, because we know it'd have to be an equal number.
Yeah, exactly. Okay, so the whole body, we have a unknown force vector here. I'll call that RB. The roller provides a force with a known direction like this. And then we have the 1,000 and then the 200 Newton meters. And once we get to the cuts, I'm always going to use the left end point as my about point. But when I'm doing the whole thing, there's no reason we have to do that. So I'm gonna put my about point here for this one. Anyone remember why we always put the about point at the left end during the cuts? Yeah, that's all it is. It just makes the math simpler. And if you want to see it, just try it. Try a cut with your about point somewhere else once, and you'll just see how messy the algebra gets. That's all. Okay.
Initially, you hope to calculate like RBX and RBY in this case.
That's right, but unfortunately, we need to just to calculate that RA there.
Oh,
okay. Okay, so Newton's second law says 0, negative 1,000 plus 0 RA plus RBX RBY is equal to zeros. So we already know that RBX is 0. And then the moment equation, let's do about the z-axis first. So we have, and our free body diagram, I didn't take into account the fact that that pin joint at the end provides a torque. So I'll call that torque B. Okay, so we have plus or minus a 2-meter moment arm times 1,000. That would make this beam rotate counterclockwise around the red dot. Then we have plus or minus moment arm of 1 meter times RA. That would make it rotate clockwise. And then the RB is acting at the about point, so that's 0. So we have RA is equal to 2,000. And so RBY is equal to negative 1,000. And then we'll go to the moment equation. about the x-axis. The only things producing torques about the x-axis are the 200 in the negative x direction and the torque provided by the pin joint. And so TB is equal to positive 200 Newton meters. Okay, so now we have all the external loads. I can rewrite that again. So we have a downward force of 1,000, a torque of 200 Newton meters going to the left, and then RA was 2,000. And then RBY was 1,000 down. And then the pin also provided this torque of 200 Newton meters. Okay, we have one point force point couple or change in the distributed load function. So one extra cut. Okay, so we have 2 cuts total. Okay, the first cut has to have its right end before you get to the 2,000. And the second cut has to have its right end between the 2,000 and the endpoint. So cut 1. This is for x's between, well, what are the ranges that the right end can be at? What are the ranges of x that this first cut can be valid for? Before 1 meter, yep. So anywhere from 0 to 1, not including the endpoints. Okay, so I'm going to draw a representative piece. And it's going to have a 1,000 going down here, a 200 to the left here, and then the internal loads. And the length of this piece is x, okay? Where x has to fall somewhere in that range. And this time I'm going to, like for every cut, I'm going to use my left endpoint as the about point. So I'll start with Newton's second law. We have 0, negative 1,000, plus, I'll combine the t and the v, so t negative v is equal to zeros. So t is equal to 0. V is equal to negative 1,000. And now I'll do my moment equation about the z-axis. The 1,000 doesn't produce a moment. The t doesn't produce a moment. Neither the torques do about the z-axis. So all we have is m minus vx is equal to 0. So M is equal to Vx. And so M is equal to negative 1000x. And then we'll do the moment equation about the x-axis. So we figured out that M is equal to Vx, but we already figured out what V was. It's negative 1000. So I just made that substitution. And now along the x-axis, we have the 200 in the negative direction, plus the internal torque in the positive direction. So our internal torque is equal to positive 200 Newton meters. So these are our functions for the internal loads, and they're valid on the interval from x values between 0 and 1. Okay, now we have to do our second cut. What's the range of x that this is valid for? 1 to 2, yep. So this time, we have the 1000, the 200, we have the one additional thing here. Your free body diagrams for the different cuts always have to have different features in them. Otherwise, there was no reason to do the cut, the extra cut. But this one has the extra 2000 newtons there. And then we have the internal loads. And my about point again will be this. So Newton's second law says 0, negative 1000, plus 0, positive 2000, plus t, negative v, is equal to zeros. So t is equal to 0, and v is equal to 1000. Then we'll do the moment equation about the z-axis. That 2000 is, I didn't draw this in here, but
1 meter, right?
That's right. So the whole piece has a length of x, but this piece only has a length of 1. So we have plus or minus moment arm of 1 times 2000, and that would make it rotate counterclockwise around the red dot. And then we have our plus m minus vx is equal to 0.
Is m always going to be, are you always going to put it as positive in the equation?
Yeah, because we always have it defined as counterclockwise.
Okay.
And that V always has a moment arm of X and would always make it rotate clockwise around the red dot. So that's why those two always appear as plus M minus Vx. So M is equal to Vx minus 2000. And so M is equal to, substitute the 1000 in for V, 1000x minus 2000 and then the moment equation for the x-axis, about the x-axis, we have the torque of negative 200 plus the internal torque is equal to 0. So just like with the first cut, our internal torque is equal to positive 200. And these are valid on the interval x between 1 and 2. So now we have this piecewise function that follows one function for x between 0 and 1, follows another function for x between 1 and 2, and you could plot that out or whatever. Okay, any questions about that? Yep.
I almost get confused between rotation, making the second block around X and.
Oh, okay. Well, the coordinate system we're using is like this. X this way, Y this way, Z coming out towards us. Okay, so think of, one by one, think of each one of these things as a pin, and the body rotates around that pin. So about the x-axis would be this thing doing like barrel rolls, okay? And so that's when we're dealing with the torques, like the 200 and the fancy P. About the z-axis, if that was a pin that it was rotating around, would be this thing doing flips, okay? And so that's why the vertical forces affect that, and the couples in this direction. And then we never deal with anything that would make it rotate about the y-axis. That would be like it doing side flips. Yeah. Okay. We just don't ever deal with those. And so yeah, we skip that one. Any other questions? Okay, so the last thing we have to deal with is distributed loads. So the last thing that can come up with internal loads and beams is distributed loads. And so I'm going to start with some simple ones and then move up from there. I guess we're not going to do any crazy distributed loads in this class. So I'm just going to do one that represents the weight of the object, and then I'm going to do one triangular one. And I'll just do it as examples. So let's say that we have a cantilever beam. like this. And we'll say that the length is 3 meters. And we'll say that the mass is 30 kilograms. Which means that the weight is that times 9.81, so 294.3 newtons. To represent the weight as the distributed load, divide it by the length. So a free body diagram looks like this. We have a force over here, I'll call that R. We have a couple, I'll call that reaction moment, MR. And then our distributed load is uniform. With a height of 294.3 divided by 3 meters. So that is 98.1 newtons per meter.
And that comes from the 294 point.
Yeah, 294.3 divided by 3. Well, this is one where, I say the first step is to calculate the external loads, but if all the unknown external loads are at the far right endpoint, then they're not going to come up in the cuts. So we can just jump right into the cuts on this one. So how many cuts are we going to have here? Only one, that's right. So the question is, are there any points between the endpoints where there are point forces, point couples, or changes in the distributed load function? In this case, the distributed load function is just constant the whole time. It's not even it is a function, it's a constant function. And so the whole thing is going to be represented by one cut. So our x is going to be between 0 and 3. So here's our free body diagram. And we have our internal loads. This is one where there are no external torques. So you know that torque is going to be equal to 0, but I'll just put it in here anyways. But anytime you see a problem with no external torques, you can always just do it as if there's none, like we did in statics. Okay, and just skip the rotational Newton's second law about the x-axis. And I'm going to, so before I can start doing the calculations, I need to represent that distributed load as a point force. So this distance is x. So let's represent that distributed load as a point force. So that rectangle has a length of x and a height of 98.1. And the centroid of the rectangle is right in the middle. And so the area of this is 98.1 x. It's just the length times the width of the rectangle. The centroid is in the middle, so this distance is x over 2. And so now I can rewrite so we have our internal loads. And then we have our point force right at the middle. That's equal to 98.1 times x. And the distances here are, this one is x over 2. And this one is x. Any questions? So Newton's second law, and my about point, like always, is going to be at the left end point. Newton's second law says 0, negative 98.1 x plus t negative v is equal to zeros. So t is equal to 0. V is equal to negative 98.1 x. And now I'll do my moment equation about the z-axis. So first we have a plus or minus moment arm of x over 2 times a force of 98.1 x. Would that make it rotate clockwise or counterclockwise? The key is the red dot. It has to be rotating about the red dot, so that would make it rotate clockwise. So this is negative. And then we have our plus m minus vx is equal to 0. So m is equal to v times x plus 98.1 over 2 is 49.05. And we have x times x. So now if I plug in v, plug in negative 98.1 x for v, we have m is equal to negative 98.1 x times another x, so that's squared, right? Plus 49.05 x squared. And so we can simplify this as m is equal to negative 49.05 x squared. And then we'll do the one about the x-axis. So the only moment we have about the x-axis is fancy t. That's equal to 0. So as we expected, the internal torque is equal to 0. Any questions about that? Okay. Let's do one with a triangular distributed load. So I'm going to have it cantilever on the right again. And I'll have a distributed load like this that comes up to a maximum of 500. And I'll apply a torque on this one of 300 Newton meters. And let's say the overall length is 1.5 meters. How many cuts do we need for this? Just one, because in between the endpoints, there's no point forces, no point couples, no changes in distributed load function. So my first cut is going to be valid for x between 0 and 1.5. So we have the 300 Newton meter torque there. And we have the distributed load there. And then we have the internal loads, T, V, M, and fancy T. And before we can do calculations, I have to represent that distributed load as a point force. Okay, so here's my triangle. And at first glance, you might think like, oh, this is a cut, so this length is X. Your first thought might be, okay, this length is X, that's right, and this height is 500. But the height of this is not 500 because this has to represent cuts, okay? So this length X could be 1 centimeter, or it could be 1.49 meters, or anywhere in between, you know? And so we have to represent the height over here as a function of X, okay? And so what we're going to do is we're going to calculate an equation for this line, okay? So the equation for this line is y equals mx plus b. At x equals 0, at the left end, the value is 0, so there's no y-intercept. And for the slope, we need the rise over the run. And so it goes up 500 over a distance of 1.5. And so what do you get there? So that's 333.3 repeating X.
Why being 0 again?
Because X refers to how far, like our origin is always X equals 0 here, you know? And this thing has no height at X equals 0. And so that's kind of like the definition of y-intercept equals 0. Okay. If this was going the other direction, it would have a y-intercept that you'd have to deal with.
the right side.
Yeah.
Would that also?
Then you'd have to have a y-intercept, yeah. But for the cuts, we always have our origin at the left end and the about point at the left end. So you don't have to worry about that.
That's what is that?
M is the slope of that line function. Okay, so this is what we're going to call Q of x. That is the function that defines the height of the distributed load. And now the height of this right triangle, a pretty ugly triangle. The height of that right triangle is 333.3 repeating x. The centroid is here. And we know just from the formula of a centroid of a right triangle that if this whole thing is x, this distance is 2x over 3. And the area is base times height over 2, which is 333.3 repeating x times x over 2, which is 166.6 repeating x squared. Okay. And now I can redraw my free body diagram. We have the 300 Newton meters there. We have the point force representing the distributed load here. The internal loads. And then the distances. This one is 2x over 3. And this one is x. And now we can do the calculations. Newton's second law says 0, negative 166.6 repeating x squared plus t negative v is equal to zeros. So t is 0. V is negative 166.6 repeating x squared. And then the moment equation about the z-axis. So we have a moment arm of 2x over 3 times a force of 166.6 repeating x squared. Would that downward force make it rotate clockwise or counterclockwise around the red dot? Clockwise. Yep, clockwise. The right end would dip down, so it would be rotating clockwise. So this is negative. And then we have plus m minus vx is equal to 0. So m is equal to positive 111.1 repeating x cubed plus Vx, which is minus 166.6 repeating x squared times another x. So x cubed. And so m is equal to negative 55.5 repeating x cubed. And then we'll do the moment equation about the x-axis. That's the easy one. So all we have is a positive 300 plus our internal torque is equal to 0. And so the torque is equal to negative 300. And then after you're done, there are 3 derivative checks you can make. Two derivative checks. So at each point, the derivative of the bending moment with respect to x has to be equal to the shear force. And second, the negative derivative of the shear force with respect to x has to be equal to q, that function that defines the height of the distributed load. So this is a function defining the height of the distributed load for each x. So let's check this. So dm dx, if you take the derivative of m with respect to x, you get negative 166.6 repeating x squared. And that's our v. And now if you take the negative derivative of v with respect to x, that gives you positive 333.3 repeating x. That gives us our function, where is it? Up here, that defines the height of our distributed load.
Is there any derivative checks for the 2t value?
No, not really. I mean, there could be if there was such a thing as like distributed torques, but that's not really something that comes up. Any other questions? Okay, so now that we are able to calculate these internal loads, what we're going to do for the next while is learn how to calculate stresses at points in beams once you have those internal loads. So we'll be able to go not just to calculating the internal loads at different x values, but to calculate the stress tensors at various points for a given x. And then, of course, from there, we could calculate principal stresses, strains, all that stuff. Okay, that's all. Goodbye.